bring your table, okay, of the formulas for the Laplace transform. There are going to be a couple of them that you have to use the theorem in order to find. So I'm going to give you those theorems that we're going to apply, and you start with the first one, okay? So the first one, you would like to find the Laplace transform of the following functions, okay? So this is going to be practice. Okay, so that would be practice test number 3. Okay, practice test number 3, and the question 1 is, we'd like to find the Laplace transform of each function. Find the Laplace transform of each function. You need the following formulas. Just remind you what you need. Okay, those basic ones are going to be involved, but these are the most of the new ones that we are going to question you. So the formula that we need, you need 2 translation theorem. So the first formula is the formula for the Laplace of unit step function. See, Laplace of UCT, e to the negative CS over S, with this one. Second one, Laplace transform. Yes.
This isn't like related to this, but can you also post that extra credit? The extra credit.
I may post one, yes.
Oh, you.
Yeah, I have to make one.
Oh, okay.
Yes. But yes. Yes, we did.
Is there what total of 3 extra credit assignments?
Yes, extra 1, 2, 3. How many you got? So yes.
Oh, okay.
You have it on, or you may have it on.
Okay.
Okay, but we give you 3.
No. Okay.
Usually give that one, I think, for the final.
Okay. I see.
Okay, let's see how far this will go. It doesn't matter. I have to make one because I know that I have the third one, but I have to check it. Okay. So, and that is the unit step function. The second one, the first translation. Okay, Laplace of UCT, f of t minus c when you shift the function, remember? Because of the UCT, you are going to have e to the CS again. And you have to multiply by the f of s, which is Laplace of the function, okay? When shifted t minus c, you change it into the t, and you take the Laplace, okay? So that's the second one. The third one is the other translation theorem that we did have. That is, sorry, I missed the Laplace here. Okay, so the next one is going to be Laplace of e to the at, okay, e to the at f of t. You have this this factor. So whatever you do is it's going to be f of s minus a. Okay, so this means basically you find the s, f of s, and you change the s into the s minus 1. Okay, so this is the same as f of s, but then you switch the s into s minus. Okay, this is it. And the next one is, if you have the factor, it's going to be power of the t. So if you have the Laplace of, let's say, t to the n, f of t, as soon as you see this t to the n, you have to go with the derivative of the Laplace transform. Remember? So this is going to be negative 1 to the n, then the nth derivative of the f. Okay, so that's a collection of formulas that you need to apply in order to find the Laplace transform for this question. So we give you 1 or 2 questions on these. Okay, we check all of them. And of course, you are going to check it when you get to the solving differential equation. Okay, make sure you have the tools. Now we're going to take the part 1. Okay, the part 1, the function is f of t. And the function is f of t e to the negative 2t cosine of the 4t. See it? So the extra factor is e to the negative 2. So this is the formula that you have to apply. Okay, so this is it, solution. Solution is going to be, you want to find the Laplace of e to the negative 2t cosine of the 4t. Okay, that's going to be the case. Now that this is going to be what? This is going to be the Laplace of, like this is going to be the Laplace of the cosine of the 4t. When you change, okay, when you change the s into the s minus 4. Depends how we are going to use the, okay, s to the s plus 2 side. S plus 2. Okay, or you can find the Laplace of f, Laplace of cosine first. Laplace of the cosine of the 4t is going to be what? It's going to be s over s squared plus 60. Okay, so then you are going to change the s into the s plus 2. Okay, so you change the s into the s plus 2. So the Laplace of the function e to the negative t cosine of the 4t is going to be simply what? It's going to be, you change the s into the s plus 2. S plus 2, s plus 2 whole squared plus 60. Okay, usually simplify it. So that gives s plus 2. This is going to be s squared plus 4s plus 4 plus 60. So the final answer would be the Laplace of e to the negative 2t cosine of the 4t is simply equal to s plus 2 on the top, okay, and s squared plus 4s plus 20 done. So this would be the final answer. Okay, any question? So the key is, as soon as you see this factor, it's a translation theorem. You just find the Laplace of a function, okay, and you change the s into the s minus a. This is a negative 2, so s minus negative 2 would be plus 2, and do that. Okay, that's a type 1.
Can we skip the notation and just go straight, if we can see what the answer is, can we just go straight to the answer?
Which notation?
The bar as to s plus 2. We can do that. So, okay.
I just explain it.
Yeah.
Myself, it is not the way I do it.
Yeah.
And as we go on, you will see. Drop this.
Okay, perfect.
Just the beginning. Okay. Already, that's the first one. Second one involves f of t equal to the t cube. Okay, t cube plus 2 u2t. Okay, minus 5 u4t. Unit step function. Okay, we take the Laplace transform of f of t. It's use the linearity expanded. Okay, so the solution is going to be the Laplace of f of t. It's going to be the Laplace of the first one. Okay, the Laplace of the t cubed. Laplace of the t cubed plus 2 times the Laplace of u2t minus 5 times the Laplace of u4t. That's a substitute and you get. Okay, the Laplace of the power of the t, you know that it's n factorial over n s to the n plus 1. So it's going to be t factorial. It's going to be s4. That's going to be plus 2. It is e to the negative 2s over s. And this would be minus 5. Okay, e to the negative 4s over s. Okay, on the simplification, there's 3 factorial, of course. You simplify that, give you 6 over s to the 4th plus 2 e to the negative 2s over s minus 5 e to the negative 4s over s. And then like that. You don't have to simplify this. So that would be the question involving a couple of unit step function. it's straightforward, this case. Any question? So we covered 2 of these. We need a couple of more. We're done to the next page, and we go to part C. Part C is the power of the t times the sine. Okay, so this is going to be part C. In part C, you want to find the Laplace of this function. It's a t squared sine of the 2t. So you have to use the derivative formula that you're going to have. Okay, so we find the Laplace of this one first. Okay, so this is it. Find the formula is what? It's going to be -1 squared. Okay, the second derivative of the Laplace function, if you like. Okay, -1 to the n, fns. Now we have to find this f. So this is it, the Laplace of sine of 2t. Laplace of sine of 2t is going to be 2 over s squared plus 4. Okay. And so this is going to be your fs, if you like. You can use different notation, you know, it's okay, you know, they call it f. You may call this one g, it doesn't matter as long as you know what you're talking about. Okay, so if you call this one f of s, then you have to differentiate it twice. So the first derivative, you can use the quotient rule. It's going to be the derivative of the top times bottom would be 0, bottom top. So that give a -2s times 2 divided by the bottom square, s plus 4 all squared. So you simplify the top, that gives -4s, -4s over s squared plus 4 all squared. Okay, that's the first derivative. Any question? Since you want to differentiate again, you better move it up. It's easier to differentiate it rather than the quotient rule. You don't need to simplify the final answer. So we get the f double prime. F double prime of s, I'm sorry, I moved this one up, -4s times s squared plus 4 all to the -2. Differentiate this one, use product rule, which is easier. So the derivative of the first times second, -4 times s squared plus 4 to the -2 minus derivative of a second times first. You know that's going to be -2 times -4s would be positive 8s. Okay, times s squared plus 4. You drop the power into -3 times the u prime, which is the 2s. Just use the chain rule. Differentiate u to the -2. So -2u to the -3 times u prime. Okay, just a little bit of simplification and you're done. Change those negative powers. So this is going to be a -4 over s squared plus 4 all squared. And over here you multiply the monomials together. So that give you 2 times 8, 16. 16 s squared over s squared plus 4 all cubed. Okay, so in the formula, -1 squared is positive. So that basically is going to be the final answer. Okay, so the Laplace of t squared, you don't have to rewrite it, I just do it. It's going to be, you don't have to simplify these final answers. It takes times and we are not going to use it anymore. Okay, just make sure you remember one case from each of these formulas that I gave you. Okay, any question? So that was the case with the differentiation. We go to the part, okay, part D, again, is just a differentiation case again. So in part D, the function is f of t equal to t cosine. Since the power is 1, you just need the derivative. Okay, so if you like the Laplace of t cosine of t would be -1. -1 times f prime, which is a negative f prime s. Okay, but you have to find the Laplace of that function and then differentiate. Okay, so there you are. We find the Laplace of cosine of t, which is easy, s over s squared plus 1. This is going to be your fs. You differentiate it and you're done. Since it's just t, you differentiate it once. Okay, quotient rule. F prime of s is equal to the derivative of the top times bottom would be s squared plus 1. Top the bottom times top will be minus 2s times s divided by the bottom squared. So on the top, we get s squared plus 1. Okay, s squared plus 1 minus 2s squared divided by s squared plus 1 all squared. And if you simplify the top, so f prime of s is going to be something like 1 minus s squared, okay, divided by s squared plus 1 over squared. Okay, that's it, but we did have a negative sign here. So you apply that negative sign and you are going to declare the final answer. So the final answer would be the Laplace of t cosine of t is going to be equal to, I just apply that negative sign, negative 1 minus s squared over s squared plus 1 whole squared. Apply the negative sign on the top, you get this formula, t of the cosine of the t is equal to the s squared minus 1 over s squared plus 1 all squared. This is a popular formula. There are a couple of differential equations, a couple of them, in application cases that when we solve it, and at the end, we want to find the Laplace inverse, we will get this one. So it would be, it would be good if you remember this one or make a note somewhere. There is going to be one there are two in your book. When you get to this one, you arrive at this. You know that for the Laplace inverse, you may try to say, oh, I'm going to factor it, partial fractions, etc. It's a very popular case. That is s squared minus 1. There are two popular ones. It's 1 over s squared plus 1 all squared. And the other one is s squared minus 1 over s squared plus 1 all squared. We will get it when we get to that solution of the equation. Okay? So it's not bad to have it available in case you need it. Okay, so that's part D. Any question? So we are not going to go higher the power of the t because it takes times. Okay, so t squared, these are going to be the case that we're going to have. Okay, so that's part D. Now the other case is going to be all of these two questions. This is, we're going to check it and we check one question on the final of this. Okay, so the other one is have a kind of a piecewise defined function that you have to change it to the U type yourself. Okay, so we start with this one, h of t. So h of t is this function. H of t is 0. Okay, it's going to be 0 when t is less than 2. Okay, and we did this one before, but I just repeat it. It's a t greater than or equal to 2. Okay, that's your function. Of course, one way to do it is just using the formula, the definition. But you should change it to the unit step function. The definition takes times. Okay, so we would like to change it to the unit step function. Okay, for the unit step function, you know that you have the 0, 1. So change this one into the 0, 1. You can factor this one out, make it to the 0, 1, and then take care of the rest. Okay, so solution. This is it. So think about h of t as the factor of the t minus 2 squared. So that give you 0, 1. Because you multiply by the top, you get the 0. If you multiply by the bottom, you get t minus 2 squared. Okay, t less than 2, and the t greater than or equal to 2. Now, as you know, this is going to be what? This is a unit step function. It's going to be unit step function, and this is going to be u2t. That's it. So the function in question is h of t equal to, like we can write them as a u2 of t times t minus 2 all squared. So it's exactly the setting that we can do it. Remember, UCT f minus c, the formula that we need have. Okay, therefore the second translation theorem, just do it right away. Okay, so this is it, Laplace of h of t is going to be equal to, you see, because of the u2 over here, you have a quotient of e to the negative 2s. Laplace of this function, this is a shifting of the function. You shift it to the 2. So the function is just t squared. Okay, it's a t minus 2, call it t squared. So it's going to be Laplace of t squared. Okay, they must be the same so that you have the form of the theorem, okay? And the coefficient is, the factor is e to the negative 2s, the function is t squared. So it's going to be e to the negative 2s, Laplace of t squared, 2 factorial is going to be the 2, and that give you s3. Okay, so basically the Laplace of h of t, the function it's given to you, is going to be, in this case, simply 2e to the negative 2s, negative 2s over s3, and then you there. Okay, it's going to be very short, but you should recognize it in the case. That's a unit step function, and yes.
Do we not have an S underneath the e to the negative 2s
No,
like that other one?
E is part of the formula.
Okay.
See, it's e to the negative cs Laplace of. Remember, it was fs. Then I change it to the Laplace of the function. Okay. The only time that you have to divide by s when it's a unit step function by itself. UCT. Okay, so that's a part E. We have another one, part F. Part F, the function is the h of t. It's very popular property. Cosine of t on the top. Okay, t is less than or equal to 1. Here we have a t minus 1 as cosine of t. Then the t is greater than 1. Okay, it's greater than or equal to 1 here in this math. Okay, that's it. Again, of course, you have to change it to unit step function to be able to do it. So you need 0 on the top here. So we have kind of subtracted cosine, take it out. So we can take out the cosine t from there. We have it down, up and down. So we can take out the cosine of t up first, out. Okay, not as a factor, in this case, as a sum, if you like. So the solution is going to be, this is h of t. Take cosine out. That seems is a plus. It's going to be plus. Okay, plus at the top. Now this would be 0, because 0 plus cosine t would be cosine t. And over here we get t minus 1. T minus 1 when t is less than 1 and greater than or equal to 1. Okay, any question? Now we have to take care of the second part. Second part, you need 0, 1. So we just factor this one out. Okay, so we continue. It's going to be cosine of t plus t minus 1 out. Then the leftover is going to be this function. You get the 0 when t is less than 1. And you get the 1 when t is greater than or equal to 1. And we test it, check it again. You multiply these two together, give you 0. If you multiply this one, that gives you 1. So this is going to be your u1t. Okay, so finally, the function is this. So we get h of t equal to the cosine of t plus, you see cosine of t plus u1t, t minus 1. See, the second part is just the formal form of the translation theorem, okay? So we take the Laplace of cosine t is s over s squared plus 1. Over here, because of the u1, we get e to the negative s times the Laplace of the t. This is t minus 1 when you shift it. So there you are. Laplace of h of t is going to be equal to. Okay, so that give you the Laplace of s of t cosine t, which is going to be s over s squared plus 1. The Laplace of the second one plus, because of the u1, you get e to the negative s. Okay, e to the negative x, Laplace of the function, but this is the shifting one, t minus 1. You got a t, so it's going to be times that by Laplace of the t. Okay, Laplace of the t, e to the negative cs fs. Okay, so we have to find the Laplace of the t. So the final answer will be s over s squared plus 1. And this will be plus Laplace of t is what? Is 1 over s squared. Yes, so it's going to be e to the negative s over s squared, the final answer. Accepted. Okay, any question? So these are various formats that we can have, to take. And we are not going to give anything else, other categories, because the other one you are going to do it when you go to the solving the differential equation. But these are unique. Yes.
Isn't the Laplace of t minus 1 1 over s squared minus 1?
No. You don't break it. You see, this is not your function. Remember, this is f of t.
Oh,
minus
right.
c. You have to. This is the shifted one.
Right.
You have to replace it. Okay. Replace it by t. T minus 1, call it t. Okay, so that's the first category. Any question? So that's first one. The second group, and the next one is the other way around. Laplace inverse. Give a couple of the easy one for this case. Okay. Mostly are going to be fractional one, fractional form. So that was question number 1. Question number 2, Laplace inverse. Okay, this is the one that we have. Okay, so these are the functions that we consider. The different format, that the first one is the one that you break it into 2 parts. This is that the one you have translation one, and this would probably the one that you have to make completing the square method. 3 standard. Okay, let's do it one by one. I explain it for you. So find the Laplace inverse or the inverse. Find inverse. The inverse Laplace transform. Laplace transform. Inverse Laplace transform of each function. Okay, of each function. That's it. Take them one by one. The first one is very standard. F of s. Okay, f of s is equal to the 2s minus 3 over s squared plus 4. Okay, this is very popular case that we have. Graph s squared plus 4 done the denominator, you know that. If you have only a number on the top, that can be done by the sign. If there is going to be s on the top, this can be done by the cosine. You have both of them together, you have to break it first. Okay, so that's very standard operation there. Most of the time. Okay, there you are. So we rewrite it. This is going to be fs equal to. So the first one would be 2s over s squared plus 4, and that would be minus 3 over s squared plus 4. Okay, then we can do it right away. You can take this 2 out. The first one is going to be cosine, but the second one we wanted to be sine. Remember, it's a over s squared plus 4. A squared is 4, so you need a 2 on the top. We create that 2 as we go on. Okay, so there you are. So the Laplace inverse of fs is going to be equal to the first one. Get that coefficient out, 2 cosine of the 2t. For this one, you don't need a 3, which is on the top, and you need a 2 on the top. So what you do, you divide by 2, and then you declare this one to be sine of, sine of 2t, and you're done. Okay, any question? In case of the sine, you must make sure that that a is on the top. A is 2. You don't have it, you divide, multiply. Like when you do the integrations, okay? So I divided 2 here because I need 2 on the job. And that's it. So that's the case 1. Any question? It's very popular case. Most of the time we're going to operate this one. Now, the second one is going to be the one that we need the translation theorem. We have 2 translations, so we give. So the function is f of s equal to f of s equal to the e to the that e to the negative 3s, e to the negative s over s squared, s minus 2. E, that factor of the e represent uct. It's e to the negative 3t, so that represent u32. When it's a u3t, and the rest you just find the, okay? So for the rest, you have to find your Laplace transform first, okay? And then you change the s into the s minus a. So this is going to be the formula, if you like the formula. So this is the Laplace inverse of fs. It's going to be equal to, okay, so basically, because of the e to the negative 3t, it's going to be u3t. Okay, it's going to be u3t. I'm going to call this one something like, j of s minus 3. So this means where is the j? And the j is js, if you like, is 1 over s squared, that's s minus 1. Okay. Oh, I'm sorry, I made a mistake. I'm sorry. I should say, this is the second tranche, f of t minus 3. You see, this is the one that, because you have the u3t, when you have a u3t, u3t ft minus c, u3t ft minus c. And so what we are going to do, in fact, I don't want to be confused with this notation, okay? So call this one lowercase g of t minus c. Because it's unfortunate that we use the f for this one, we have to break it apart, okay? So this is it, you work on this, you check the denominator, it's factorable or not. In this case, I think it's factorable, yes, so that's not.
It's supposed to be negative
Oh,
2.
this must be 2. So it's factor, it must be factor. Okay, you factor in x plus 2 times s minus 1. Okay, since it's factorable, you have to do the partial fraction one. Short form, going to be what? It's s plus 2, and this is going to be s minus 1. 2 opposite number on the top, it doesn't matter what it is. So I put the 1 and negative 1, negative 1 and 1, doesn't matter. Now we check it. If you find the common denominator, the top would be what? The top would be s minus 1 minus s minus 2. Negative 1 times s plus 2. So these 2 would cancel out. You get negative 3. And you need a positive 1 here. So what you do is you go back and you divide each one of them by negative 3. Negative 3, negative 3. So the partial fractions are going to be negative 1/3 s plus 2 plus 1/3 s minus 1. Okay, you may have to do this one several times on the test, so you better use it. Okay, any question? Very happy about it? Because there is a number here, the s must cancel out. Since you want to cancel out the x, you put the 1 and negative 1 on the top, it doesn't matter. First one, negative 1, the second one. Then you do it. You see 1 times s minus 1, negative 1 times s plus 2, that gives negative s minus 2, so the result will be negative 3. And you want, when you find the common denominator, you want the top end up with the 1. So that's why you normalize it. Divided by negative 3. So this factor must be negative 1/3, negative 1, negative 3 will be positive. Okay? Now we are ready to take the Laplace inverse and then we're done. Okay, so what is the Laplace inverse of that function, or just, we have, this is it. Laplace inverse, I call it g of s. Okay, so this would be the Laplace of the first one is a negative 1/3 e to the negative 2t, and this is going to be positive 1/3 e to the t. So you're going to take it up here, okay, up here, and you're done. Okay. So if you like, this is the one we call it G of t. So the final answer is Laplace inverse of f of s is going to be u3t, g of t minus 3, okay, when g of t is equal to the negative 1/3 e to the negative 2t plus 1/3 e to the t. Okay, this is a shorter version to write it down. Otherwise, you have to change the t into the t minus 3 all over the places. But whatever you call it g of t, and you have to shift it. So the shifted one would be gt minus 3, accepted. Okay, so that was part B. Any question? So if you have this factor, if it's going to be factorable, this is the way we're going to do it. It's going to be the second translation theorem. We need one more. The one that the denominator is not going to be factorable, and you have to use the completing the square method and the other translation. Okay, are you ready? So that was the part, okay, part B. We need the part C of this problem. Part C, we want to find the Laplace inverse of this function. Okay. Part C. Part C, the function is f of s equal to 1 over s squared minus 4s plus 5. I think it's not factorial. This is the case. Okay, you need two numbers with product of 5 and the sum of 4. It's impossible. So do the, okay, just do the completing square type. So this is the way you are going to look into it. It's going to be 1. I repeat it, s minus 4s plus 5. Remember the way we do it, we divide this coefficient by 2. That gives you negative 2. So you write s minus 2 all squared. But now you owe something. When you square it, s squared, 2 times first times second 4s plus 4. So you owe 4. Owe 4 means minus 4. That's it. It's going to be minus b squared all the time. Balance it. And the plus 5. Now you simplify it, so that gives you 1 over s minus 2 all squared plus 5. That's it. So you call s minus 2 s squared. You have 1 over s squared plus 1. 1 over s squared plus 1 is, okay, it's going to be Laplace of the sine t. Okay, is going to be sine of t, but you have this translation that you're going to have, and you have to apply that. Okay, so this is going to be, the translation that you have is e to the 2t. Okay, so the Laplace inverse of s is equal to Laplace inverse. I'll show you how to do it. 1 over s minus 2 all squared plus 1. That's the way you think about it. Since you have a shifting over here, okay, if you have the shifting over here, so the result would be what?
E to the
You have
2t.
e to the 2t, and the leftover would be simply sine t. Okay, if there was something like u function, then you have to apply that to the other theorem. Okay, so 2 translation theorem, 2 examples. That's it. Yeah. Okay, any question? So far we got 3 questions for the test. Okay, 3 questions. 2. The first group are quite a lot. 1 from each. So it's going to be 2 on 2 questions, and this one is shorter. 1 question, 2 parts of this. Now, we are going to give you something to prove for us in this test, okay? It's going to be involved Laplace transform. And this number 3 is a very nice application of the Laplace transform. I prove it for you. Of course, I'm not going to give you this one to prove. But there is a conclusion of this result, which is quite interesting for calculus. That will enable you to, Okay, enable you to find some very complicated integral in calculus. So I may give you that integral and ask you apply the Laplace transform to find it. Okay, so I'm going to show you this. This is one of the famous application of the Laplace. Nothing to do with the differential equation, of course. But we want to see the this nice application. Okay, there you are. This is a number. Look at this. We explain it over here. I list a couple of results for you because I wanted to go through it. The one that we are going to be interested in part C. You can make a note of the part C and use it anytime you like. You see, this is part C. If you want to find integral of 0 to infinity f of t over t, simply integrate the Laplace transform of f of t, which is on the top. Done. Okay, if you want to find the integral of 0 to infinity, f of t, t dt, or any function you like. Instead of finding this integral, you simply find the integral of 0 to infinity, the Laplace of the top. Done. Great result, okay? There are 5 famous integral in calculus, and you won't be able to do it. But with this one, just a matter of second, and you do it. So for example, look at this one. This is one of them. 0 to infinity sine t, t dt, you want to prove it's a phi half. Check on internet. There are various proofs of this one, but you have to know something about complex variables, complex analysis, and something we call it contour integrals to be able to do it. In calculus 2, what you do is this is improper integral. You just using comparison test, you prove that this is convergent. Means there is a solution, but you won't be able to find that solution. But look at this formula, compare them together. You want to find integral from 0 to infinity sine t. Look at this. So in this formula, your f of t is sine t. So instead of this integral, you find integral from 0 to infinity, Laplace of sine t. What is the Laplace of sine t?
1 over s squared plus 1.
1 over s squared plus 1. So you find integral from 0 to infinity, 1 over s squared plus 1 ds. What is this integral? Give us a function whose derivative is 1 over s squared plus 1, or 1 over x squared plus 1.
Arctan.
Tangent inverse. Would be tangent inverse. You find it from 0 to infinity, would be pi half. Just only 2 seconds. But I can show you the proof that, I teach from time to time complex analysis. I will show you the proof that how we do it over there. It's a kind of long 1 page and quite a lot of mathematics to be able to do it. So it's a great formula. So that's why we wanted to know it really. And you can use it in application problems. And I know 4 more, so I give you one of them on this test, okay? But you know everything now. Do it. But make sure that this is it. Whatever it's on the top, find the Laplace of that. So we have to have something nice to be able to find the Laplace, and something nice to be able to find the integral.
So it has to be over t. Whatever you give us has to be over t.
Yeah. You can't do it. Yeah, it's going to be over t. You can have some other, but just over t. We just wanted to see the taste of these type of ideas really. There is a reference to this one. Is a paper. If you go back and check, the paper was published in 1946. Somebody came with this idea that Laplace transform, we can use it to do this type of ideas. Okay, so in some of the books they talk about it. So it's not bad to see. Okay, so I quickly give you how we prove it, but you don't have to know the proof because I prove it for you. But you have to know this result. If I say apply the Laplace transform to find this integral, that's it. This is the only way you can do it. Okay, there is a list of the function. Okay, so let's do it. This is it, number 3. So number 3, what I just list the result that we have, but the one that we are going to be interested in is in part C. Okay, so I want to prove this one for you. You make a note and use it anytime you like on the test. So I want to prove that integral from 0 to infinity, f of t over t dt is simply equal to the 0 to infinity. You see, I write f of u over here, it doesn't matter, f of s, f of t. Since eventually you go where I just remind you that you have to find the Laplace transform. So I call it f of s ds. It's a name. We call it f of z dz. As long as the variable and the differential are the same, you are fine. And that gives you a better idea that this is basically what? This is basically the Laplace of this function. Okay? Now, to prove it, you have to go through these. Just remind you that, see, the solution is going to be, note that we did this one, okay? I proved this one before for you. So that's a part of one of this problem, that the Laplace of t, f of t, that's the key of this problem. You see, this is a negative f prime of s. Remember, this is the one that we already proved for you. Okay, so we proved this one. So that will help us. We want to make this f of t over t to see what is going to be. So that's part one. It's already proved, you have it. So that's done. So what I'm going to do now is I'm going to find what is the Laplace of f of t over t using this formula. Then I get integrate. Okay. So in the part B of this problem, you are interested to find what is the Laplace of f of t over t. Okay. Want to find this one? Okay. So what you have to do is you have to get the connection with this. How are we going to use this one in order to find the Laplace? Yes.
T to the negative.
Yeah, what he said.
Which one?
T to the -1.
So
f of
what?
t. So it would be like, instead of derivative, it would be like an integral.
No. The only thing that we want to use is this one. We don't have anything else. How are we going to use this
1 over the
to
Laplace,
find the Laplace of f of t?
1 over Laplace f of t,
1 over,
Laplace f of t, no?
no, the connection is going to be,
So
let me
then
just
it's-
remind myself, so I just proved it here. So what we can do is, you see, look at go back and make this one. See, this is the way I did it. So see, in this formula, this is true for any function, f of t. So what I can do is I can change this f of t into the f of t over t because I want to find the Laplace f of t. Okay, so if I change this one into the f of t over t, what is going to be the result that we have? You see, look at this one. Suppose I'm going to call the Laplace of f of t over t. It's going to be a function of, okay, I'll call it g of s. Just for simplification, okay? And then look at this. I'm going to go to this formula and replace f of t by f of t over t. It's going to be the result. It's going to be Laplace of t as is. So I change this function into what? Into the f of t over t. So what would be the other side if I do this one? Is minus derivative of which function?
1 over f prime, that's 1 over
You
f
see?
of t over t over.
Derivative of the Laplace of f of t over t. This is the one that I call it gs, prime of the gs. Okay, so it's a t f of t. You can use any function you like. So I use f of t over t. Okay, but that will help me because these two would cancel out. Okay, these two would cancel out. The result would be what? Would be Laplace of f of t is equal to the minus g prime of s. Okay. So if I multiply by a negative sign, so that gives me g prime of s equal to the negative Laplace of f of t. But remember, Laplace of f of t is just f of s. So what I have I have g prime of s equal to the negative f of s. It's like a differential equation, or it's like the antiderivative. So integrate both sides with respect to the s. This would be out, you see, integrated. Doesn't matter. I use the interval of a to s, g prime of s ds. This is going to be negative integral of a to s, f of s ds. Remember, you want to end up with this integral eventually to get your result. Okay? But this part is going to be what? This part would be g of s minus like a g of a. And on the other side, we get negative a to s f of s ds. Just usual practice of integrations. So what I'm going to do, we need integral from 0 to infinity. So I take the limit of both sides. A goes to positive infinity. When a goes to positive infinity, this would be 0. Because we arrange it over here, you see that this would be 0, and this part would be just integral from infinity to s. So what is going to be the result? I write it in here so that you have it and you see it. So I will end up with this. G of s is equal to the negative integral from infinity to s, f of s ds. But s is a positive number. Infinity to s doesn't make sense, but there is a negative here. I switch the limit of integration, that give me g of s equal to what? S to infinity, f of s d of s. But what is g of s? G of s is the Laplace transform of f of t over t, which is going to be integral from, okay, integral from s to infinity, f of s d of s, okay? This is going to be f of s d of s. Almost there. Okay, any question? So this is, so I proved that the Laplace of f of t is going to be s to infinity f of s ds, but what you need the integral of this part. So change it to the definition of a Laplace transform. What is the Laplace transform of f of t over t? See? So I repeat it again. I have Laplace of f of t over t is what is integral of s to infinity, f of s d of s. The definition of Laplace transform is what? 0 to infinity, e to the negative st ft over t equal to what? Equal to the s to infinity f of s d of s. And this would be true for all s greater than or equal to 0. Any question? Yes,
How many proofs are on the exam?
1. Okay, we are not done with this. Okay, let's go. So any suggestion? So what we want to prove is, we want to prove 0 to infinity. F of t over t is 0 to infinity, f of s ds.
Let's make S 0.
Excellent. Make s 0. Because true for all s. S equal to the 0. 0 to infinity. F of t over t. Of course, there was a dt. dt is equal to the 0 to infinity fs ds. Great theorem. I published that. I post that paper for you, the original one. The guy who proved it, so you can see what they did years ago. Okay, so you can use this one anytime you like. We would like you to use it. Okay, so this would be a kind of application of, as we can see, this is the function, this is the Laplace of the function. That's why I use these notations. So this would be given to you. What you have to do is to forget about the t. You just find the Laplace of the top, You bring it here and you integrate it, and you're done.
So is that the question that we have to do a proof, or is that just another question that we have to do?
No, we would like to apply it.
So that's the proof.
Yeah, because the proof, I proved it for you. So I want to know if you are, you can use it.
So we don't have to do any proof ourselves, actually, if we know this.
Not for this one, yeah.
Okay, cool.
Yeah, I wanted to see it. It's a nice proof.
It's a very nice
To
proof.
see, yeah, to see how they connect. That's a great result. Because obviously we're just using, some people think that Laplace transform is used only for solving differential equations. If you do more, if you go a little bit more, you will see everything is Laplace transform.
But on the test, there is a proof, just not this one.
Not this one, no, I have another one. Okay, but remember, the one that you are going to prove for us is just a definition of a Laplace transform. Nothing complicated.
Okay.
Nothing complicated. So don't try to do something strange. Okay? We just want to see what is your understanding of, writing a proof of this type of ideas. Okay, so let's get the price. The price is this next set. Okay, we give you this type of question. Very easy integral, that's part D. And this is the way we are going to ask you. Apply the Laplace transform. Probably it's in your book, one of the problem in your book. Okay, but you may check if you see any other similar one. Apply the Laplace transform. It's the way we ask you. To show that or to evaluate this integral. See, let's say the value, the integral. The integral in this case is there are a couple of, like this one, but we want to do 0 to infinity. Sine, sine x sine t over t dt. Don't try to find it, of course. You can't do it. The way we do it, we use the integration by parts to raise that power up. When you raise it up, that gives sine t over t squared, then we use the comparison test. If you use the comparison test, sine is less than 1, you end up with the integral of 1 over t squared, which is convergent. So we can say that this integral converges, means there is a solution. You can't do anything else at this level. Okay, so don't try. So we just use this one. That's it. Bring it in, we accept the solution. This is the application. Say note that, that's it. Note that integral from 0 to infinity. F of t over t dt is 0 to infinity fs ds. Laplace transform. Now you compare. Okay, you compare them together. See, this is it. This is 0 to infinity. Sine t over t dt. So you compare them together. You see, this is your function. So your function would be changed into 0 to infinity, Laplace of that function. Laplace of, Laplace of a sine of t, then the ds. That's why I changed the notation on the review is u. I just changed it to the s so that you know that. Okay, so you continue to the right. Continue to the right, 0 to infinity. Laplace of a sine is 1 over s squared plus 1. Yes. Now whatever you have, you integrate it. It's very easy integral, whatever problem we give you. Okay, so this is going to be, you know that this is going to be limit just as in calculus, 0 to something like b, 1 over s squared plus 1 ds. E goes to infinity. You have to change it to the limit form. And then it's going to be limit of, so this is going to be tan inverse. Okay, tan inverse of s. S going from 0 to b, then b goes to infinity. Okay, so that gives you limit of, it would be tan inverse of b minus tan inverse of 0. When b goes to positive infinity. Okay, tangent of 0 is 0. So the tan inverse of 0 is 0. Okay, and when b goes to infinity, that gives you tangent inverse of infinity, which is by half. That's it. So the integral from 0 to infinity, sine t over t dt is going to be equal to the exact written here. 0 to infinity, sine t dt is going to be equal to the okay, among the proofs that they exist. But this integral, this is the shortest one and the easiest one to understand. Okay, so we make something up similar to this one. There is another famous integral that in calculus, if you want to do it, you go around. See, you may have to integration by. There are some of them in calculus too, and you want to do integration by parts, then you have to go. See, it's getting worse than the previous part. So they can be done. Okay, so just wanted to say it, just to give you, I don't know, how we ask you to prove something, because there are lots of proofs, so why not? One easy one to prove. Okay, and there you are. This is number 3. I can give a short break, then we do differential equations. Differential equation, 2 types. The first one, no translation theorem, nothing is needed. And the second one is the one that's going to be more involved. You need a step function. So we may give you one from the ordinary one, because homogeneous one. Give you 3 equations to solve for us. Okay. So we check all these properties. It will be very similar. Okay, can I have a short break and then I'll continue to use the solution.
Oh.
After this one, 4 weeks till finals.
Remember one series solution. I have your quiz, if you haven't got it and you want to have it.
Oh, those were really interested. Let's wait tomorrow, till tomorrow. The same thing.
That's 265 only. Oh, you didn't get it? Did you get the other one?
Yeah.
Oh, I was not sure which one.
Thank you.
Yeah, I think so.
Nice.
Make sure you study it for the one of those series will be.
Yeah, last one was pretty hard, so.
Yeah, we may give you the type 1 rather than type 2. Did you get that?
I have not looked at the email you sent me. But we've been very hard at work on the, just the 4A in general. I didn't know if you want to talk right now or later. We have many questions and questions, but also stuff we've been working on and stuff we want you to check and stuff.
Oh, okay.
So we've been hard at
Yeah,
work.
very good. Yeah, that was just the. The kind of version 2 that we talked
Okay, I'll give it a read right now.
about. Yeah.
Because I forgot to set it equal to 20. Literally, I made that mistake on the first exam. True, false, false, true.
Second exam, third exam?
Second exam? Yeah. I got a 99. Yeah, sure.
99.
It's
the one that worked
Huh?
last
What'd
year.
Dude, you know how you do cosine plus sine? My dumbass put cosine minus cosine. That's pretty cool. Otherwise, I would have got it.
He loves this one. He loves it. I'm gonna put this one.
Is that the formula for the second derivative?
It doesn't open.
And then it's like S minus F minus
I
F
think it's
prime.
slightly bigger.
No, it's just that, right?
Oh, F prime is 0, yeah, okay,
Yeah.
okay. I'm pretty sure that's it. I was like, there's something missing.
People are using the first appeal form to see if they got it or not, but like. the appeal form
He's on
doesn't work
option
for
one.
any- It's not bad. It's like 5%.
So wait, 1 series, 1 proof, 3 DE, that's 1, 2, that's 5. There's 3 to 4, he hasn't said it.
I was like, oh, my sister goes there and I want to be.
Okay, so differential equation, two groups. The first group, we almost have done all of them. I'll try the second one, second group. But I did all of this the other day for you. Give you a quiz, okay? There was a misprint for part C, so I updated again. It's y of 0 equal to 0, y prime of 0 equal to 0, 1. Okay, so these are going to run straightforward. Yes,
And the second one, is it supposed to be y prime?
yes. The second one is y prime. Yeah, thank you. We did this one the other day. You have it. Okay, and when I complete the list, then I bring those solution that we did the other day, so we can have all of them in one setting. So let's focus on this second group. We give you 2 questions on this. Okay, the one that is involved all those translation theorem that we did have. Okay, you need a step function, everything. Okay, so this would be the type 2 one. So let's try. So this is going to be solving each differential equation. Part A and C, and we did the part B. I will post that extra one for you, so we get something to practice, something new, okay? The point, okay? So this is it. You want to solve each differential equation. Okay, number 5. Let's see how far we can go. So this is it. Solve each equation on Laplace transform. Bringing this piecewise defined function is very popular case. You get one of them. So that's it. The first one, part 1. The function is what the equation is y double prime plus y equal to the h of t. The condition is y of 0 equal to the 0. Okay, y prime of 0 is equal to 1. And then they have to give you the h function. So the h function is this one. H of t is equal to, it's a piecewise defined function. The first part is 1, and t is between 0 and 3 pi. Okay, 3 pi and is equal to the 0, and t is greater than equal to the 3 pi. Okay, this is the one. So when you see this type of problem, you better find the Laplace of h of t first. Because when you get involved, okay, you will have to substitute it. So you better find this one first. Okay, so the solution is going to be find the Laplace of h of t first. Okay, that's it. Of course, a direct method is one of them, but we try to change to the unit step function. The unit step function starts with the 0, 1. This is 1 and 0. So if you remember, that's a complement of the unit step function. It would be 1 minus UCT. Okay, because you have to switch it. So you note that this is it. You note that. You note that your function is h of t is equal to the 1 minus UCT. Because this is a start with the 1, it just pull out the 1. It's going to be one class, if you like. Okay, and then you substitute to get these information. So that will help you, but the c is 3 pi here. So it's going to be 1 minus u 3 pi t. You get your function. Okay, any question? So this is going to be the case because the UCT started with 0. So 1 minus 0 would be 1. And the second part of the UCT is 1, 1 minus 1, would be 0. Okay, so it's gonna be the complement of the UCT. So you find now you can find the Laplace of h of t. So Laplace of h of t is going to be what? It's going to be Laplace of 1. Okay, Laplace of 1 minus Laplace of u3 pi t. Okay, Laplace of 1 is 1 over s. And the unit step function, you know that e to the c is 3 pi, e to the negative 3 pi s. Okay, 3 pi s over s. Yes,
So when there's no t minus c, then there's an s underneath.
that's it. Yeah.
Okay.
Okay, so this is going to be Laplace of h of t. So you make a note and then you start working on the equation because you need this one. Okay, it's e to the negative. Is the negative cs over s? The formula c is 3 pi. Yes.
What is y of 0 and y prime of 0?
Y prime of 0 is equal to, what is the,
Y prime of 0 is equal to 1.
y prime 0 is equal to, thank you. Okay, it's equal to 1 and the other one 0. Okay, now go back and start working on the equation. Okay, call the solution f of t and continue. So suppose y is equal to the f of t with f of 0 equal to the 0 and f prime of 0 equal to 1 is a solution. Okay, suppose this is going to be one of the solution or the solution. We'll go back to the equation, take the Laplace transform. It's going to be Laplace of, you see, f double prime of t plus f of t. So f double prime of t, okay, plus the Laplace of f of t. And this is going to be equal to the Laplace of h of t. So we have to change it to the formula. Remember, it's the second derivative, so it's going to be s squared. S squared Laplace of f of t, okay, minus s f of 0 minus f prime of 0. The second one as is Laplace of f of t. On the other side, you already got it. 1 over s minus e to the negative 3 pi s over s. So initial conditions, f of 0 is 0, so this would be 0. F prime is 1, so that would be 1. Okay, so we end up with s squared Laplace of f of t, okay, minus 1 plus the Laplace of f of t, and is equal to the 1 over s minus e to the negative 3 pi s. Okay, as usual, factor out Laplace of f of t, so the result would be s squared plus 1, which is characteristic equation of that homogeneous equation. You see, y double prime plus y equal to 0. So this means so far we are right. So move the 1 to the other side. So Laplace of f of t, Laplace of f of t. So on the other side, we get 1 plus 1 over s minus e to the negative 3 pi s over s. Okay, that is what we get so far. Now divide both sides by s squared plus 1. Yes.
Why is it not 2 over s? Why is it 1?
Why? It must be 2. Where is 2?
Because you brought the 1 over from the left side to the right.
That's 1 plus.
Well, why don't you do like 2 over s?
Where is the 2?
Because you, instead of making it 1 over s, it's just 1.
Laplace of
original.
1 is 1 over s.
Yeah, but when it's just originally 1 and then you add the 1 over, and then don't you take the Laplace?
You add the 1 over and then you're gonna divide by s squared plus 1.
I don't know what's your problem. There's no 2 here. It's algebra. You see the Laplace of 1, you see this.
Oh, wait, never mind.
Okay?
Yeah.
Are you happy?
Yeah.
Okay, divide. Okay, so Laplace of f of t, just divide one by one, okay? So it's a 1 over s squared plus 1. Okay, plus 1 over s times s squared plus 1, okay, minus e to the negative 3 pi s times s squared plus 1. See, that would be the leftover. Now f of t would be Laplace inverse of this. So f of t will be the Laplace inverse of the first one, 1 over s squared plus 1, which is easy. The second one would be Laplace inverse of 1 over s times s squared plus 1, that you have to do the partial fraction for. Again, it's easy to apply. And this one is just the transformation of the second one. Okay, it's a Laplace inverse of e to the negative 3 pi s, okay, s over s squared plus 1. See? If you do the second one, the third one, e to the negative 3 pi s, we tell you that, okay, we tell you that there was a unit function, unit step function. So there has been a u 3 pi t. So this would be u 3 pi t, what, g of t minus 3 pi, and the g that you have to find is here. Okay, all of them at the same time are going to be coming together. So if you do this one, this would be what, u 3 pi t, whatever you do over here, just multiply by the, okay, t minus. So let's just do it. You will see it in a minute, okay? So there you are, the one by one, you take care of these. The first one is easy. So Laplace inverse of 1 over s squared plus 1 is going to be sine t. That's the first one. For the second one, you have to do the partial, which is easy to do. Again, for this one, are you done? To go to the next page, I take care of this. As soon as I have this, I change the t into the t minus 3 pi, that give it the second part. For this type of problem, it's always the case. Okay, so I have to find the Laplace inverse. I have to find the Laplace inverse of 1 over s squared plus 1. You can use the shortcut to break it. It's 1 over s times s squared plus 1. So it's going to be s squared plus 1. See this one? The quick way to do it is there is no s here. Okay, there is no s here. This is the way you can cancel it out if you like. So in order to cancel the s, you have to cancel the s squared here. So you put the s here. You see, s times s would be s squared. Now, if you put the 1 here, so what's going to be the situation they're going to have? The situation is going to be, this would be, you have to put the negative 1 here because you want to cancel the s. So if you do the top, what is this? It's going to be s squared minus s squared minus 1. You see, s squared minus s squared minus 1. So the result would be negative 1. You need the positive 1. So go back and divide it by negative 1. So it's going to be what? So this is going to be how you do it. 1 over s minus s over s squared plus 1. Okay, so these are easy and it's going to be no stuff that I'm up this. Any question? Yes.
I did it just the way you would do it with partial fraction decomposition, and I got negative sine t.
Negative.
Negative sine t.
Okay.
But it's like nothing I did was wrong mathematically.
Let's do. You do it, then you decide.
Okay.
Okay. So that's what it was. So there is nothing wrong with this one that we did so far. Okay. So this is going to be what? So the Laplace inverse would be Laplace inverse of s squared plus 1. It's going to be what? You get 1 over s. Okay, so this is going to be Laplace inverse of 1 over s minus this. Okay, so Laplace inverse of 1 over s minus the Laplace inverse of S over S squared plus. You know that 1 over S would be 1. Okay, Laplace of 1 is 1 over S. And this would be what? This would be cosine t. That's it. If you do a little bit of trick, you get sine of 2t. That's easier. What you got?
I got just sine negative sine t.
Which is right. You have to check it again. Okay,
Yeah.
you have the evidence. All right. Okay, you probably missed something. Okay, so remember, if you want to do the partial fraction, this is how we're going to do it. You put the A1 here, and this is going to be A2S plus A3 to be able to take care of it. Then you will have, but you know, these are popular method. We do it right away. Okay, so this is it. So what I'm going to do it, I'm going to call this one something like G of T. If I call this one G of T, automatically I have the last one. You see the last one is what? E to the negative 3 pi S over S squared plus 1. Remember, because of the E to the negative 3 pi S, we have a unit step function. U 3 pi T. U 3 pi T is what? The Laplace inverse of this function, and you change the T into the T 3 pi. So the Laplace inverse is GT, so this is going to be G of, okay, T minus 3 pi. So if you go to that function that you have, change the T into the T minus 3 pi, you get this right away, okay? You can do it if you like, but you know, it's short. You can write on this version. So the final answer is going to be this one. F of T is equal to, remember, we did have sine T to start with. Sine T, that was the first one. The second one was plus. It's going to be plus the 1 minus cosine T, 1 minus cosine T. Okay, and then it's minus U 3 pi T, if you like, G of T minus 3 pi. You write it in this form, you have to introduce the G. You say that when G of T is equal to the 3 minus 3 pi. If you don't like it, you want to write everything, this is it. F of T equal to sine T plus 1 minus cosine T minus U 3 pi T, okay, times that by, okay, sorry, G of T, that's not correct. G of T was 1 minus cosine T. See? So if you like to repeat it, it's going to be 1 minus cosine of T minus 3P. This is going to be the final answer. But if you write GT minus T, 3 pi, you accept it right away. Okay, any question? So these type of problems, the type 2, they are going to be all involve this type of activities. Okay, but they are going to be connected to each other. They're not going to be very much way out, if you like. So that was y double prime. We have another one. Try that one too. Okay, it's a part C. It's very similar, but your equation is different. Okay, so it takes a little bit more time to do this part. The type is different. Okay, so one of these categories. Any question? So when you practice a couple of them, they are very nicely organized. Then you are not going to be surprised, and then you'll be able. But you have to practice because they take time. Okay, to do it. Y double prime plus 3y prime plus 2y is equal to the h of t again. But in this case, y of 0 is 0, y prime of 0 is 0, and you have the h function, which is similar to the one that we did. Okay, h of t is 1 when t is less than 10, And it's 0 when t is greater than equal to 0, okay? So again, quickly, you can see that the Laplace of the solution, you can see your function is not 0, 1, it's 1, 0, so the complement of the unit step function. So h of t is going to be 1 minus u 10t. Okay, make sure don't miss it. Right at the beginning. If it's a 0, 1, it's a unit step function. It's a 1, 0, the complement. Okay, so get the Laplace of h of t, which is going to be Laplace of 1, which is 1 over s, and the Laplace of the u, which is e to the negative 10s, okay, divided by s. So this is the Laplace of the u function. Go back, get the Laplace transform. So we suppose we have a solution. I changed the notation, okay. Suppose y equals to the f of t, and the condition of f of 0 equal to 0, f prime of 0 equal to 0 is the solution, okay, is a solution of the solution with this condition. So take the Laplace of both sides. So we are going to have the Laplace of what? F double prime of t, okay, plus 3 Laplace of f prime of t, plus 2 Laplace of f of t, equal to the Laplace of h of t, which is 1s minus 1 e to the negative 10ss. Okay, I just take the Laplace of both sides quickly. Okay, change those derivatives. So that gives you s squared, the Laplace of f of t minus s f of 0, okay, minus f prime of 0. We have 3 times the Laplace of f prime, would be plus 3s Laplace of f of t, okay, minus 3f of 0, and plus 2 Laplace of f of t, which is 1 over s minus e to the negative 10s over s. Okay, I just multiply together. Laplace of the f prime is Laplace of f of t minus f of 0. Okay, this is it. So get the initial condition. F of 0 is 0, so this would be canceled out. F prime of 0 is also 0, so this would be 0 too. Okay, so this would be 0. 0? Yes. Nice. Okay, so pull out the Laplace of f of t. This is 1, 2, 3. That would give you that characteristic equation. So s squared. Okay, it's going to be s squared plus 3s, s squared plus 3x plus 2. Then Laplace of f of t. Okay, so what's the leftover? None. Okay, so that would be 1 over s and minus e to the negative 10s over s so far. Okay, so that gives you the result. Okay, because everything was canceled out over here. So that's it, divide and then continue. So it's going to be Laplace of f of t equal to, divide them by, just do it 1 by 1, it's going to be 1 over s times s squared plus 3s plus 2. See, that will be repeated here again. It's e to the negative 10s s squared plus 3s plus 2. Okay, that's it. So f of t would be Laplace inverse of these two, which are connected to each other. If you find the first one, then use the translation theorem to get the second. So it's going to be minus Okay, Laplace inverse of 10, sorry, negative e to the negative 10s over s times s squared plus 3s plus 2. As soon as you find the first one, we call it g of t. The second one will be what? u10t g of t minus 10. You're done. Because of that translation, you see, because of this factor of the e that you have, okay, over there. So it's just e to the negative 10s. Okay, any question? You have to find this Laplace. You have to do the partial fractions. But this one is unavoidable. Okay, so check this. It's going to be 1 over s squared plus 3s plus 2. Inside 1 is factorable. So it's going to be s times s plus 1. S plus 1 times s plus 2. So we have 3 factors. So we have to break it. So that gives you s plus 1, and s plus 2. I have to call it A1, A2, A3. Just do it. There's no shortcut for this one. Okay. So stay to the right, find the common denominator, let them two cut each other. You have to do nice numbers, and you can find it. Okay. So if you find the common denominator is going to be s squared plus 1, s plus 2, the top. You get the A1 times the other denominator, which is s plus 1, s plus 2. Okay, we get the A2. The other factors are going to be s plus 2. And we get the A3, other factors, s times s plus 1. That's it. Let them equal to 1 and just find these 3 numbers. Okay, so there you are. A1 times S1 plus S2 plus A2, A2S times S plus 2, and we get the A3S times S plus 1, everything equal to 1. You need 3 numbers to check, and you already got the numbers. Zeros of the denominator. Let S equal to 0. So this would be A1 times, okay, times 1 times 2. Everything else would be 0 because of the S equal to 1. So that give you 2A1 equal to 1. So A1 would be half. This is the A1. Okay, any question? Put S equal to negative 1. Negative 1, you get 0 here. The second one, A2 times negative 1 times negative 1 plus 2. This is also 0. So what we have? It's a negative 1 plus 2 would be a positive 1. So negative A2. Negative A2 equal to 1. So A2 would be negative 1. Okay. And the last number, S equal to the negative 2. If you put the negative 2, the first one would be 0. The second one would be 0. Last one would be A3 times negative 2 times negative 2 plus 1, which is 1. So negative 2 plus 1 would be negative 1, negative, positive. So that gives it 2A3 equal to 1. So A3 would be half. That's it. And the Laplace transform would be easy case to find, and then get that transformation. Okay, any question? So the numbers A1 equal to the half, okay? A2 negative 1 and A3 1 half. So this is the Laplace transform, Laplace inverse of that function that we start with, okay? So the Laplace inverse of 1 over s squared, okay? S squared plus 3s plus 2 is going to be equal to the Laplace inverse of the first one, A1. Okay, A1 is 1/2. 1/2 over S. Okay, the next one, Laplace inverse of A2 is a negative 1. So it's a negative 1 over S plus 1. And the last one is A3 is 1/2, okay? 1/2 is plus 2. That's it. So the result would be, this is 1/2 of T. Because the, okay, or it's just 1/2. What is 1 over S? Okay, it's just 1/2. Laplace inverse of 1S is 1. Laplace of 1 is 1/S. Okay, that's the first one. The second one would be negative e to the negative t. This one would be 1/2 of the e to the negative 2t. That's it, call it g of t. So automatically you get the other one. So the other one is e to the negative 10s. Everything else is the same. So you get only unit step function of the u10t. At g of, you replace the t by t minus 10. So that's very quick method to do it. So finally, the final answer, f of t is going to be equal to, okay, that is two parts that we did have. So it's going to be equal to the first one, 1/2 minus e to the negative t. That's 1/2 of e to the negative 2t or g of t plus u10t g of 10 minus t. And we already give you this is going to be when g of t is 1/2 minus e to the negative t plus 1/2 of e to the negative t. You have a choice. You can write it down, list it together. T goes to negative 10, or just do the brief form. Okay, that's it. The part B, I did it during the lecture. Check your lecture notes that we did the other day is part B. So I will I'll put them together by tomorrow night. Whatever we did on the other one that we have, so you have collection as a practice.